Or this microphone, any
Okay.
microphone in the room.
How's the audio on Zoom? Can you hear me okay?
We may not
Yes.
hear them in return,
Okay.
but we're getting thumbs up. So that's
Okay.
good. Okay.
So yeah, we can't hear them, but they can hear us. That's
Yep.
okay.
That's fine.
So
We could hear them. We could turn it up if they're going to be participating.
maybe during the Q&A we'll turn
Well,
this.
so it's kind of manual and it's slow, so I'm just going to turn it down.
Okay.
I'm going to kind of
That's fine. Yeah, we're working it out right now.
We can make it, or see, once you hit play, you'll get
I'll look up the CV on my phone right now.
presenter mode.
Okay.
And if you like, we have a laser pointer and a presenter.
Yeah.
If you accidentally hit the bottom button and the screen goes blank,
Okay,
push it
I'll
again.
touch base with you at the end. I have to look up Paul's CV really quickly.
The moment your screen's going to go off in a few minutes, but I think this will kind of zoom into the podium, kind of plus or minus person. Is that enough, or do you want a wider angle? Okay. Yeah, not a problem. They all know about the lights. Oh, well, the last part, only audio that goes into a microphone is heard on Zoom. So for questions, usually I just whoever is run around and shut the microphone in people's faces. I think that'll be on you since you're holding the
Got it.
This is not
You do the lights? Okay, thank you. Ready to go?
Wasting time.
All right. Hello, can you hear me? Welcome back for third colloquium of the semester. This week we have Professor Paul Hayne from our own APS department, and I'll give you a little bit of Paul's background. Paul was an undergrad at Stanford University, graduating in 2000, some odd number at the end, 5. Long time ago. And while there, he worked with Norm Sleep and Jack Lissauer. For those of you on the planetary science side of the divide, you will know those names very well. And then he went to grad school at UCLA and worked with Dave Page at UCLA. And graduated in some year that is a number less than 2023. And then after that, did a postdoc at JPL Caltech. At Caltech, I just looked at this a few minutes ago. A postdoc at Caltech with Odetta Harrison, also a well-known name in planetary science for theory type stuff, and then on to a position as a research scientist at JPL. Paul joined us as faculty in the department here several years ago, and he is giving a colloquium today in part because he loves the department and wants to tell us about what he's been working on, but also because it is tradition in the department when you are going up for tenure or for promotion that you give a colloquium. And so this is his tenure process colloquium. So let's welcome Paul.
All right, thanks very much, Dave. So I wanted to start off with this image because it reminds us of a couple of things that I'll talk about in this lecture. One is that you can see the moon in eclipse, which is the passage of the moon through the Earth's shadow. And that reminds us of the moon's proximity to Earth and space, and also somewhat of the heritage or ancestry of the moon as being originally part of the Earth. And so I think, the moon holds a special place in the hearts of all human beings, and also especially human scientists. So planetary scientists use the moon as a cornerstone or a touchstone for understanding other planetary bodies in the solar system. And I'll touch on some of those aspects in the talk. The other thing you'll notice in this image is a lighthouse. And the lighthouse represents navigation, or navigating through difficult or dangerous waters. And so we're going to touch on that as well in this talk. That's not working. So humanity's first view of ourselves from the moon came from Apollo 8. This was taken on Christmas Eve, 1968. You'll see that the Apollo 8 astronauts have all kinds of poetic things to say about this view. It's such a famous image that it has a name like a work of art. It's called Earthrise. And everyone who has ever existed or will exist is in this frame, except for the 3 astronauts on board the spacecraft. Okay. So one interesting thing to wonder about is I showed the moon in eclipse as viewed from Earth in the previous image. What would it look like to see an eclipse of Earth, or an eclipse to be in the shadow? That's what I'm trying to say, from the vantage point of space, looking back at Earth. In fact, this was captured by another mission, Apollo 12. So Alan Bean, for those who don't know, was also an artist. So after his time as a NASA astronaut and going to the moon on Apollo 12, Bean dedicated most of the rest of his life to painting. And this is a painting that he did in 2001 based on memory of his experience seeing an eclipse, seeing the Earth in eclipse as the sun passed behind the planet. And he describes this in extraordinary detail in his memoir. There's some very interesting features of this. One is that you can see the sunlight coming through the limb of Earth, not just in a single direction, but refracted all the way around the planet. You can also see a bright spot in the middle of the Earth. Any ideas what that is? It's not a camera flash taking a picture of. What's that? I'm not familiar with that one. Okay. Diffraction effect. Okay. I am familiar with that. Yeah. So no, this has nothing to do with geometric optics. It has to do with what's actually being reflected. So the astronauts were en route back to the Earth, and this is a reflection of the full moon. Okay. So the full moon is behind them, and Bean talks about this, saying it took a while for them to realize what that bright spot was, and when they did, it was very profound because they just left this moon and they could see it reflected in the Earth in front of them. Okay, so with that introduction, I want to describe generally what I want to talk about today. So this is not just about the moon, although the focus will be almost entirely on the moon. But the context for this in planetary science is that the polar regions of planets are the coldest parts of planets typically, and that makes them special because they contain sensitive recordings or records of climate variations on planetary bodies, and this includes the moon. And yet often these climate records are long-lived, so as long as the temperatures have been stable where those deposits exist, they can last for geologic timescales. Condensed volatiles are therefore a record of climate change, and if that weren't the case, then the volatiles would not be there. The condensed form of them would not be there. So the variables that are at play here include the composition of both the atmosphere and the volatiles themselves, and also the thermodynamic conditions during which the climate variations occurred. And time scale is critically important. I'll talk about that in this talk. So ice tends to record shorter time scale variations in climate than rocks, but you can also see a vast range of time scales of climate variations recorded in the ice itself. Finally, to emphasize one of the main points of this presentation is that the current race to the lunar South Pole that we're currently experiencing is predicated on the existence of ice, and yet there's still a lot we don't know about these putative ice deposits. And I'll describe some of the uncertainties in this talk and maybe leave you with a little bit of doubt about the direction that things are headed. I wanted to introduce my research group, and I have to say that it was agonizing trying to decide what to talk about today because our group spans such a wide range of different topics. And the unifying common thread is the study of ice and climates in the solar system. And I chose to focus on the moon because that's something that I believe is going to change dramatically the study of ice on the moon in the next 5 to 10 years. But there's a huge range of other topics being studied here. In planetary science, we often encapsulate the reach of our science by the number of missions we're involved in. Okay, and so this is just showing some of the missions that my group is involved in or has been involved in, which you can see touches on many planetary bodies throughout the solar system, and again, the focus being on ice and the history of climate. Since I don't have time to talk about Mars, I'll say that one of the main focuses of my group is studying the climate history of Mars. And one thing that's very exciting is that this Mars Reconnaissance Orbiter spacecraft has now been in orbit for nearly a Mars decade. And so we're starting to get to the point where some of the climate cycles that I've been mentioning are now being observed by a climate observing satellite in orbit around Mars. So we have a continuous climate record for nearly 20 years at Mars at this point. Okay, so the way that I set up the abstract for this talk was talking about the polar exploration of Earth. And you can see Antarctica in this mosaic taken from space imagery. This is this whole period of exploration culminated in what's called the heroic age of Antarctic exploration. This was after a period of Arctic exploration that led to kind of a fervor in Europe about trying to explore these uncharted regions of the planet, with the ultimate prize being the South Pole. This was financed through a combination of public and private enterprise. So the Royal Navy and the Royal Geographic Society contributed most of the funds. The equivalent cost in today's dollars is about $2 billion as a percentage of the US GDP, which is a significant amount of money, but it's small compared to the NASA budget. So this is just a snapshot of the end of this heroic age of South Polar exploration, which did not end well for everyone involved. In fact, it didn't end well for most of the people involved. So the Terra Nova was Scott's ship. This is the British expedition on the bottom here, and this is the Norwegian expedition on the top. And you can see that Roald Amundsen looks much happier than his British counterparts here. And the reason is that these two expeditions took very different routes to the South Pole, with Amundsen arriving just a matter of weeks before the British expedition. And the British explorers didn't know that until they got there, basically. So when they got to the South Pole, they were expecting to see this desolate landscape and to have to hunt for the location of the exact South Pole, but instead they saw a flag. And in fact, all of the men in this photograph died shortly after this photo was taken on their return route back to their ship at McMurdo Station. I'll just point out where that is here. So McMurdo Station is over here, which was the base of the Scott expedition. Okay. So very treacherous stuff. Why explore the poles in the first place? I want to provide a scientific rationale that has nothing to do with necessarily the human drive to explore, which I also think is important. But the reason this is important scientifically is because the poles are, as I said, the coldest parts of planets, and they record these climate cycles that are the most important drivers of long-term climate change on Earth and also on other planets like Mars. The polar ice deposits record these climate variations, and they can be measured by collecting and sampling that ice. And of course, these are often the most inaccessible regions for human exploration. So we see a variety of appearances of the polar regions of planets in our solar system. I'm going to focus on the moon and other solid bodies in the next few slides here, but I wanted to show the polar vortices of the planets with atmospheres in the solar system. So you can see this very rich variety of atmospheric dynamic processes, but the fundamental process going on here is that the warmer parts of the planet are trying to reject heat or get rid of heat, and that heat is transported to the colder part of the planet. The Coriolis effect causes the rotational motion of the circulation in these planetary atmospheres that then creates what's called a polar vortex over the polar region. This isolates cold air, and it also can create what are called cutoff lows, which then affect the weather in places like North America. So you can see that all these planets with atmospheres have this same kind of pattern. On planets without atmospheres or with thin atmospheres, it starts to get interesting in terms of the exchange of volatiles between the atmosphere and the surface. And this same thing happens on Earth. A big difference on Mars is that the main constituent of the Martian atmosphere, which is carbon dioxide, actually freezes out at the poles of the planet. This is a similar process to what we think goes on the Moon with water, which is why I'm highlighting it here. The pressure curves that are shown on the screen show the variation in pressure recorded by the Viking landers at 2 different elevations on the surface over the course of 1 Mars year. And so that variation records a 30% change in the mass of the atmosphere of Mars over the course of a seasonal cycle. The volatiles, the key thing here is that volatiles in a planetary atmosphere will condense at the coldest location on the planet over a given time scale at the expense of the atmosphere or other warmer locations with condensed volatiles. In other words, if you have 2 ice deposits, on average, the warmer ice deposit will lose mass and the colder one will gain mass. That's it in a nutshell. Getting into a little more detail, the saturation vapor pressure controls how much of the material is evaporating or sublimating from that condensed phase, and that will be controlled by the saturation vapor pressure at the coldest location on the planet. So the mean vapor pressure over some time scale, that's what I'm calling delta T, little t, is going to be equal to the saturation vapor pressure averaged over that time scale at the coldest location on the planet. Okay. This is important because it means that the temperatures of the coldest places on any planet will control how much ice condenses given an amount of vapor available in the atmosphere to condense, basically. So on the seasonal time scale, 30% of the Martian atmosphere condenses on the 1 year or 2 year time scale. But over a million year time scale on Mars, you have even more dramatic changes where you get a factor of 2 change in the mass of the Martian atmosphere. And we now think that a large part of that total amount of CO2 is contained, locked up in the south polar ice cap on Mars today. So something very similar is going on the Moon, as you'll see. So this has dramatic effects. And just to illustrate this. So if you draw a line across, just take an average of this total pressure, which at these elevations is 7 or 8, 9 millibars, that is the saturation vapor pressure at the temperature of the south polar ice cap of CO2 on Mars. Okay, so the permanent cap of CO2 buffers the atmospheric pressure. This has dramatic effects on both the circulation of the Martian atmosphere, including dust storm activity, snowfall. So we've done studies in our continuing studies of the snowfall processes going on at the south pole at both poles of Mars and their impact on the energy balance and so forth. So Mars is a very good example of this kind of process in action. On a planet with a lower atmospheric mass, things change a bit, but fundamentally they're the same. And what this is showing is essentially on that equation for m dot is the rate of change of the condensed phase, which is in this diagram here, is proportional to the saturation vapor pressure at the given temperature of that solid, but minus the available gas in the atmosphere, basically. So if there's nothing there, if it's in complete vacuum, that PV goes to 0, and the saturation vapor pressure completely controls the sublimation rate. When there is vapor pressure there, then you get this exchange between the condensed phase and what's in the atmosphere. So the Moon must have gone through periods where the saturation, where the available vapor in the atmosphere was not 0. The water in the atmosphere was sufficient to supply some portion of that water to the surface. How long that occurred and how much condensed is a critical question for this next phase of exploration of the Moon, which I'm going to spend basically the rest of the talk on. The temperature where this happens, so if you have ice under vacuum, the temperature at which it sublimates is around 110 Kelvin. And the important thing here is that it doesn't really matter what that exact number is, because if you look at this plot here, these are evaporation or sublimation rates as a function of temperature. this is a logarithmic scale, and these curves are basically vertical even on a logarithmic scale. So if you're on the right side of the curve, then the volatile is unstable in its condensed phase. If you're on the left side, it behaves like a rock. Okay, you can do this for any volatile you wish. This was the context for one of the major discoveries in planetary science in the last few decades, which was the discovery of polar ice caps, or massive ice deposits at the poles of Mercury. And these had been predicted on the basis of what I just said, and also the fact that Mercury has permanently shadowed craters. I'll describe what those are in a moment, but follow-up observations with Arecibo showed these glowing bright regions right where we'd expect them to occur if Mercury at one time had sufficient vapor in its atmosphere to condense water in the coldest places. And we see deposits of tens or hundreds of meters of ice in these permanently shadowed craters. So the current picture of where ice exists in the solar system has sort of expanded. So we see buried ice on Earth to some extent too, but the presence of an atmosphere certainly affects where ice is stable. So buried ice is stable, somewhere in the terrestrial planet zone and beyond. Surface ice really only becomes stable again under vacuum at the orbit of Jupiter or beyond. And then we have this shadowed ice, where as long as you're in a permanent shadow, or at least a long-lived shadow, ice can be stable all the way into the orbit of Mercury. And this is quite interesting from the perspective of mixing of material in the solar system, which may come from places where these volatiles are stable in their condensed phase, such as through comets coming into the inner solar system, colliding with Mercury and delivering material that could then be studied up close without having to go to a comet. So this is sort of how we think this works on the moon. At least this is the canonical view that I'm going to cast doubt on later. But you see these ballistic hops. Once a delivery mechanism occurs, and these are summarized over here, you get these hops of water molecules around the lunar surface, which then eventually, if they're lucky, before they're destroyed by the sunlight, they end up in a cold trap. So some of the sources that we want to investigate include comets and asteroids, both of which can be water-rich. The solar wind provides ample protons, which can interact with the lunar surface and produce H2O. And then also the moon's interior. So outgassing from volcanic eruptions on the moon can also produce large quantities of water. I just see some chat messages here. I just want to check this real quick. Okay, so something's been fixed. Great. Okay. So the old terra incognita was Antarctica. The new terra incognita is the poles of the moon. And this is just a beautiful image from the Lunar Reconnaissance Orbiter showing the dramatic difference between the sunlit surface of the moon and these permanent shadows. So why do permanent shadows occur? They happen because the obliquity of the moon is close to zero. So basically, in its inclined orbit around the Earth, the tilt of the lunar spin axis is such that basically the direction to the sun is at an angle of about 1.5 degrees. So the solar declination on the moon oscillates between plus and minus 1.5 degrees roughly over the course of the month and the year. So what that means is that if you drop down into a crater at the pole, the sun is revolving around the horizon, but the walls of the crater will block the view of the sun. So these are places where the sun literally never shines. And so you can see this is a sped up animation of the actual illumination at the moon's south pole, which happens to be on the rim of this crater called Shackleton. Most of the craters at the poles of the moon are named after some of the explorers from the Antarctic and Arctic expeditions. So you can see this incredibly complex topography, which then generates an incredibly complex distribution of shadow and light. In addition to the permanent shadows, we also have regions that are in permanent sunlight or very close to permanent sunlight. And those are very interesting from an exploration standpoint as well. So my involvement in lunar science was a bit reluctant, actually. As a graduate student, I didn't have any particular interest in the moon. And I was nearing the end of my graduate career. I was already writing my dissertation. I was kind of at the stage in your career where you're questioning everything and do I really want to do this? And I was very fortunate that I happened to go to Florida early. My PhD advisor, Dave Page at UCLA, invited the whole research group to fly out for the launch of Lunar Reconnaissance Orbiter. He was the principal investigator of the Diviner instrument, still is. And so a bunch of us flew out early to try to catch one of the last launches of the space shuttle. Happened to be around that same time. And so I was literally laying on a beach when my phone rang, and it was Dave. And he said, "Hey, Paul, are you in Florida?" And I said, "Yeah." And he said, "Well, I'm not there yet, but they want me to go on this VIP tour to go into the vertical integration facility and see the rocket. Would you like to go?" And I dusted off the sand and ran back to the hotel room, and I found the one pair of nice pants that I had and put them on. And I just wanted to show this because it really was a pivotal moment in my career as a student, and I, in my career now, try to give these opportunities to students as much as I can. And I think those of us who have access like that should do that. And it really reignited my passion. I got to go up and I took this photo, and I got to put my hand on the upper stage of this Atlas rocket. This is called the Centaur, and that was what they used in the L-Cross mission, which was piggybacking on LRO to crash into South Polar permanently shadowed crater on the moon and measure what came out. I'll describe that in a minute. Diviner was on the main spacecraft up in this payload fairing, and Diviner, at the time of the L-Cross impact, which happened just a couple of months after lunar orbit insertion for LRO, there was no plan that I could ascertain on the Lunar Reconnaissance Orbiter team to actually observe the L-Cross impact. Okay, so L-Cross had a separate spacecraft that was going to watch the rocket crash into the moon, and they were going to observe with spectrometers and all the rest. But LRO had this whole suite of instruments, and there was no plan to look at the impact. So I was a measly graduate student. I said, maybe there's something we can do. Diviner it's a thermal infrared radiometer multispectral instrument that has the capability to scan in both azimuth and elevation directions. And so my advisor said, well, why don't you design some scan sequences that would allow us to observe the impact, And I was starting from absolute scratch, okay? I had no idea how to do this. So I went to, I came up with the correct rotation matrices and all the rest that we needed to do to rotate the spacecraft. And we were about to uplink the commands to do this. We had just a matter of days to do this targeting. And we were at the AAS DPS meeting, which happened to be in Puerto Rico that year. And from the hotel room, Dave Page said, shouldn't we do some kind of dry run before we do the actual event? Let's upload the tables for the previous day, maybe, or previous orbit. It was the previous orbit, that's right. So the orbital period is 2 hours long, so we had a 2-hour window between the two. So I wrote the script to do that. We sent it to JPL, they uplinked it. We got the data down on the next White Sands pass, and we were pointed in the wrong direction. it was like a sign error, So I found the sign error, and we had 20 minutes until the next pass to uplink the commands for the next orbit, and we did it. And I'll show you, it was a direct hit. Okay, so the L-Cross spacecraft this is up the upper stage, coming in at 2.5 kilometers per second, targeting this region in Cabeus crater, which is one of the coldest places on the moon that also has one of the highest hydrogen enhancements based on neutron spectroscopy. And this is the Diviner data sweeping across here, and so we hit it right on. And this is, you probably can't see it in the back of the room, but there's a little, so this is temperature, basically. It's a brightness temperature in a particular wavelength. But you can see a little pinprick of light right at that arrow, and that's the glowing hot crater from that impactor that hit, basically. There you go, yeah. That's not the temperature of the glowing hot crater because it's subpixel. So the glowing hot crater from this we were able to determine was initially about 1200 degrees C, and then it cooled off to a few hundred degrees after we actually saw the glowing crater on multiple orbits, basically. And we also estimated the amount of water that was produced through the sublimation of the water in the subsurface as that heat wave propagated downward. All these results are summarized, here and here. The cool thing was that, so the L-cross experiment itself saw these, or the spectrometer saw this fairly dramatic rise in the amount of water vapor after the impact, and that's consistent with about 5 to 7 weight% of water in the regolith at this particular site. We also, before the impact, based on temperatures that had already been measured by Diviner, we predicted some other species that may be delivered by comets. Those are here, and those were all detected in the same spectrometer data. There were 2 very interesting compounds that were detected in the L-cross plume and with LAMP, which is the UV spectrometer on LRO, which were not predicted. And this is a challenge to anyone out there who would like to explore an unsolved problem, basically. We don't know why there's condensed methane and molecular hydrogen at this site. It was about 45 Kelvin at the time of the impact. The maximum temperature is like 90 Kelvin. These things should only condense at temperatures of 10 or 12 degrees, so above absolute zero. So we're confused by this. Okay, so that's a snapshot of where things kind of were before I came to CU Boulder, and I wanted to summarize some of the current directions that we're going in, including some recent work that casts doubt on the whole paradigm of lunar ice, but also presents some opportunities to test this new model that I'm going to present here. So I'll talk about a couple of different problems with the current model. So the current model, again, just to remind you, is that water molecules bounce around the lunar surface in the exosphere, and eventually, if they're lucky, they make it to a cold trap. We've observed the composition of those cold traps. So this is a view of the South Pole with the Diviner temperatures in the background in grayscale, and the blue points are detections of water at the surface. This is just one of the data sets that's been used to identify water frost in the PSRs, permanently shadowed regions. But what you can see here is there's this heterogeneity. So in other words, not all of the PSRs contain the same amount of ice. In fact, some of them look quite bare. This is not what you'd expect in this kind of model. So in other words, if there's a continuous supply of water, then all of the cold traps, as long as they're colder than that 110 Kelvin cutoff, should be equal. They should all accumulate ice at roughly the same rate. And that's not what we see. So this implies some kind of anisotropy in the source or loss process, or at least local scale variations. And this also suggests the supply and destruction of the water may be in some kind of equilibrium or close to it. Otherwise, you'd have either none or all the cold traps full. The other problem with the current model is that there doesn't appear to be any appreciable water in the lunar exosphere. So this whole thing, this business about water bouncing around the surface, implies that there should be water in the lunar exosphere, and that has not been detected. In fact, we can put limits on it, and Dick Hodges and others have done that, of less than 6 water molecules per cubic centimeter. This is an incredibly small amount, which basically means, and this is an upper limit, which basically implies that the lunar exosphere is dry, okay? The other aspect of this is that during the Apollo missions, there were measurements taken from the lunar surface, again summarized by Dick Hodges, showing the surface-bound exosphere of argon went through a diurnal cycle. Okay, and this was repeatedly observed. And so the argon cycle, and stay with me for a minute, the fact that argon is cycling up and down means that argon must condense at night. And if it's condensing on the night side, that means that there must be bonding sites for the argon with sufficiently high activation energy that it will remain there during the night. And so there's this diurnal cycle of argon. Okay, so you have these sites where argon can condense. Those sites should be extra sticky for water, okay? And that's the gist of this argument, that if argon can condense, then water should never leave the surface. And so therefore, you can't have water bouncing around on the surface like this because the surface is just too sticky for water, okay? Finally, the last problem with the current model or current paradigm is this apparent young age of the lunar water. So it turns out those ice deposits on Mercury, we have good reason to think that those are quite young, actually, because of the sharp boundaries and various cratering observations you can make on the surfaces of those ice deposits. So it's not out of the question that the lunar water could have been delivered relatively recently in geologic terms. But we're talking very recently in the case of the moon. So Bill Farrell and others, and I'm among those others, have published on this rate of destruction of water on the lunar surface. And the lost processes of water should dominate over the known sources of water in a continuous long-term sense. So again, the time scale of this equilibrium matters. So over a long time scale, you should have more destruction than delivery. And so the lifetime of any water that's injected into the lunar atmosphere and then on the surface should be less than 1 million years and maybe even less than 100,000 years. And so why do we see any water on the surface at all? It should be gone. So relatively recently, Lior Rubinenko and other, Lior sitting in the back of the room here, have looked at the possibility of buried ice. And there's quite a bit of circumstantial but very compelling evidence that there is buried ice under the surface. The first evidence comes from the depth-diameter ratio of craters on the left here. So both on Mercury and the moon, we see a decrease in the depth-diameter ratio of the craters as you go to the poles. Well, what does that imply? That means the craters are getting shallower as you get close to the poles. What would that imply in this model? Ice, yes. I'm just making sure you're still awake. Okay. So that implies in this scenario, it implies that they're infilled with ice. And in fact, you need about 10 or maybe 100 meters of ice to fill in those craters. So that's kind of shown here, basically. So, and then there's been other work showing that essentially the topography and the surface roughness is subdued inside these permanently shadowed regions of craters, implying that perhaps there's some ice or a different kind of material underneath the surface. So we're presenting here a new model for lunar ice. The model here, and this is the reason I'm presenting this in this talk, is because we think this is testable during the Artemis missions. I'll describe how that can be tested. So there is no continuous source of water on the moon, okay? It was delivered at some time in the past, and this buried ice results from the transient accumulation of volatiles at the poles, either through volcanism, so the release of water from the lunar interior, or through cometary or asteroid delivery. Okay, so you have these spikes or transient influxes of water. Those get trapped at the poles during big events, and then that ice is sequestered over time in those PSRs. The surface water ice detections are real, but those surface water ice detections are the buried ice being exhumed or exposed onto the surface. Okay? And then impact gardening and burial are basically stochastic processes at some spatial scale. I mean, you can get this kind of heterogeneity, but also, importantly, temperature is scale dependent and location dependent. And so you can get very different temperatures at very small scales, and so we should expect heterogeneity in the amount of ice from one location to the next. Okay, so once on the surface, the ice is rapidly destroyed, and so these things must be in some kind of balance. So we want to test these theories. So the first part of this is whether you can produce a deep deposit of ice through these transient events. And my former student, Andrew Wilkowski, who defended last fall, investigated this along with Margaret Landis, looking at the formation of ice deposits in the permanent shadows during these transient events. So in the case of lunar volcanism, Andrew looked at the amount of water that would be produced by eruptions and how thick of an atmosphere that would produce. And we were surprised at the size of these atmospheres. So basically what ends up happening is you get these events that produce Mars-like atmospheres on the moon for thousands to tens of thousands of years. The escape is actually quite slow because of the moon's significant gravity. And so those atmospheres are collisional. So they're like they would flow, basically, like the Martian atmosphere. And so Andrew modeled in detail the circulation and condensation of the ice from the atmosphere, the water from the atmosphere. And what he came up with were the maps at the bottom right here, showing that you could get tens to hundreds of meters thick of ice in the permanently shadowed regions during these events, basically. Simultaneously, Margaret looked at the trapping of other species that could be signatures of this kind of volcanic outgassing event. So water is everywhere in the solar system, right? So it's not a very good tracer for the the source of that material, that volatile. So we want to look for other things. So sulfur is something that comes out in volcanic eruptions on the moon and Earth, and this is a good tracer for volcanic activity. There are other things that might be in higher abundance in comets, like HCN, for example. So you could look for these things in the places where they're both stable and see what is the dominant source of those volatiles. So this is one way that we can test these ideas with Artemis, is by measuring the detailed composition of the volatile deposits. Secondly, we want to test whether the existing observations of ice on the lunar surface can be explained by buried ice being exhumed onto the surface. This is the other part of the model that I've described. So we did that using a model that we originally came up with for Tara Tomlinson's work. She was an undergraduate here, now a PhD student at Dartmouth, looking at Europa. But it turned out the same model we were using for Europa was applicable to the moon. And the reason is that essentially the permanent shadows on the moon are much more similar to the outer solar system than they are to the inner solar system. So we're looking at the same kind of process that removes ice and leaves behind the non-ice material. So it turns out that you can actually solve this analytically. So looking at a certain crater production function and the distance to which the ejecta material is thrown, you can calculate the likelihood or the probability at any given time that you'd have a certain fractional surface coverage of surface ice in a permanent shadow. And so that's basically what we did. So this FE is the fractional coverage of ice over a given time interval. Okay, so the results in map form are shown here, and you can see that starting from the right, so the right-hand plot shows the actual ice detections in the PSRs. So each blue point indicates a positive detection of ice. Again, you can see they're not filling the PSRs. That's the important thing here. If we consider only thermal loss, then they're all full. I've said this before. So basically, if temperature is the only thing controlling the loss of ice, the PSR should be full of water. They're not. Now, in this model of impact excavation and then destruction on the surface, if we give the water on the surface a lifetime of about 1 million years or down to 100,000 years, we can much more accurately match the observations. So this lends support to the idea that the ice that we're seeing at the surface is literally the tip of the iceberg, that basically you've got a deeply buried deposit that's being exhumed through these impacts. And it's only through those impacts that we actually see the superficial water. And it doesn't last very long. Okay, finally, the last component of this model, and I'm going to get into Artemis and what we're going to do in the future to test these ideas. In doing this kind of work, we started to realize some time ago that the temperatures on an airless body, like the moon, are controlled almost entirely by sunlight and shadow, which means that they're controlled almost entirely by topography and surface roughness. And also, the other important fact is that if you go down to ever decreasing spatial scales, the topography increases, or the roughness increases. So slope, the root mean squared slope of the surface, will tend to increase as you go to smaller spatial scales. What this means is that you should have more shadows on smaller scales than large scales. And so when the astronauts get down on the surface, the question is, where should they look for ice, both for scientific and exploration purposes? The answer that we came up with was that, in fact, the most numerous cold traps on the moon would be those about 1 centimeter in scale, so the size of a penny, roughly. So this got a lot of attention, and it's one of these things where, when you see the media coverage of your research, it's not always like exactly how you would explain it to your colleagues. But anyway, regardless, the headline was there's more water and ice on the moon and in more places than NASA thought. That may be true, but it may not be true. And either way, the answer will be very interesting. So again, looking at the lunar surface from the perspective of an astronaut coming into land, this is what you would see at the poles. It's very different from what the Apollo astronauts saw, right? Even in the illuminated terrain, you've got craters and shadows just everywhere littering the surface. And as I've said, the temperature is controlled only by the shadowing. It's not controlled by the size of the crater. So therefore, the temperatures of these shadows should be the same or equivalent to the big, deep, dark, permanently shadowed regions that NASA has been focused on. Do they have water ice in them? That's an interesting question. So we need to go back to this idea of time scale. So these centimeter-sized shadows are indeed the most numerous, but when you look at, and this is a distribution of the number of cold traps as a function of scale, total number on the moon, so the peak corresponds to the most common spatial scale of about a centimeter. But when we look at the destruction time scale, so this is in this case illustrated by the impact gardening rate, or the overturn rate of the lunar regolith. The overturn rate for 1 centimeter spatial scale, is about 1 million years. So in other words, it takes about 1 million years for any given patch of ground to be reworked or turned over completely at a centimeter scale, okay? That's how you can read this. So that means if there's any ice in these little PSRs, these little cold traps, it must have accumulated in the last 1 million years or so. Okay, so this is what's testable about this. Okay, so they are indeed much more accessible, but if they're not full of ice, then that would help us test this idea of the young age of ice on the moon. Is it young or is it old? If it's old, then the micro cold traps will be empty, basically. Okay, so I've discussed how we can kind of use Artemis to test this. What is Artemis and what is planned for these missions? So I pulled this from an issue of Science where they were talking about the coming lunar armada. And as you'll see, this only partially illustrates what we think is coming. So you can see Apollo back here in the Russian missions in the 60s, a long gap, and then things have already started. Okay, so we've got not just NASA missions, but international missions too. I'll mention a few of those in a minute, with this big uptick in missions to the moon, both with astronauts and robotic missions. The major difference between efforts that we've seen in the past 10 years or so to do this and the current wave is that there's money behind it, okay? So I'll describe that in a minute. So the international efforts are numerous. I'm just highlighting a few of them here. So the Chinese have succeeded in doing some things that even NASA hasn't done yet, which is to bring back samples from the lunar surface. They've also landed on the far side of the moon with these robotic landers. These are also very large landers that could be easily scaled up to carry astronauts. The Indians just succeeded with their Vikram lander and the rover that was attached to that mission, landing as close to the South Pole as any mission has gone so far, at a latitude of about 69 degrees. The Koreans have currently in orbit this orbiter called the Pathfinder Lunar Orbiter. This was developed entirely within Korea based on their Earth orbiting satellite technology. It includes a NASA-contributed instrument too, so we're working closely with the Koreans on their science missions. And then the Russians, how to put this? They did not succeed with the Luna 25 polar lander. That was launched just before the Vikram lander was to touch down, and the spacecraft experienced a rapid and uncontrolled descent to the surface and crashed, basically. But the Russians still have plans on the horizon to do something similar. The drill, or one version of the drill on this mission, has been remanifested. This was contributed originally by the European Space Agency to the Luna 25 mission. It's now on a different mission, which includes an instrument from the University of Colorado that I'll describe in a minute as well. Okay, so the current phase of what we call Artemis, that includes multiple different components that I'll show in a minute, started in 2017. These kinds of directives have been made before, but there were a couple of key differences that I think are important. One is that this program was directed to be a sustainable program, meaning that it would not be a one-and-done, flags and footprints kind of mission, but it would be a sustainable effort, including both commercial and international partners. And that has been borne out. And then also the humans to the moon for long-term exploration and utilization. Again, this is not just a step on the way to Mars, but is a major program unto itself. So The components of this program include the Space Launch System, SLS, which has already launched once. That's the Artemis 1 mission, which sent the Orion capsule around the moon and back. The Artemis 2 mission will do the same mission profile with astronauts on board the capsule. It includes this moon orbiting space station called the Gateway, which is a much smaller version of the International Space Station in a lunar orbit that also enables some science to be done. And then we also have these commercial lunar landers, including both static landers and rovers. So you can see, depending on who's in charge, the moon or Mars might be bigger in this kind of diagram, but it's the same story, basically establishing a long-term presence on the moon to prepare to go to Mars. I said that I'm going to continually emphasize the science aspects of this, the science motivation, and I think there is a strong science aspect to this that we can take advantage of as planetary scientists and as astrophysicists and solar physicists as well, I'll say. So you can see these, in addition to all these major human components up here, the lunar surface in this program is just littered with robotic landers, okay? And all of these are science-driven. So there are 22 lunar lander missions, robotic lunar lander missions currently planned, about half of which have already started to receive funding, and some of them are launching in 2 months, okay? And so those 22 missions are basically sponsored by NASA's Science Mission Directorate, meaning that the science objectives of the mission are paramount, okay? So there are numerous opportunities for the Artemis program to be leveraged to do science, and some of that science leads into the issues around lunar ice and the exploration purposes that the ice may have for astronauts. But a lot of it is pure science. One example I wanted to highlight is a project that Jack Burns is involved with, ROLS's, which is just one of several of these CLIPS missions that Jack is involved with. And this is to measure galactic radio emissions at a part of the spectrum that's very difficult to observe from Earth. But on the far side of the moon, or from certain vantage points on the moon, you get a very clear view of that part of the spectrum. So this is very exciting. This is going to launch in a couple months. My own involvement in this Artemis program, again, is mainly focused on the science missions. One of the missions has already launched and failed, okay? So the Lunar Flashlight mission was one of the 13 CubeSats that was supposed to be launched by the first Artemis 1 mission. So underneath the main payload fairing containing the Orion capsule, there was a ring that contained a set of launchers for 13 CubeSats. Lunar Flashlight actually missed its ride, and so we launched on another lunar mission that launched a Japanese lunar lander from a company called iSpace, which was also unsuccessful. But Lunar Flashlight, in addition to those other 12 CubeSats, they were all unsuccessful. And the only reason I wanted to highlight it here was to show that number one, these are things that have not been done before, and so we should expect a certain amount of failure. I think 13 out of 13 failures is a bit high, but but this is when we're trying to test new technologies, and so you'll see there will be another wave of CubeSat missions. I should have said this is a CubeSat, the size of a briefcase or so. The purpose of Lunar Flashlight was to shine lasers, to fire pulsed lasers, multispectral lasers down to the lunar surface into the permanent shadows and map out in detail the distribution of the surface water inside these PSRs. And we were able to test the spacecraft. So basically, most of the spacecraft subsystems worked just fine. It was the propulsion module that failed, basically. So in almost all the cases for the lunar CubeSats, it was the propulsion system that failed. So this is like, motivation to fix this, particular technology for future missions. The second and final mission that I wanted to talk about that I'm involved with is shown here. The instrument is called the Lunar Compact Infrared Imaging System, built here in Boulder in collaboration between Ball Aerospace and LASP. The instrument itself, I'll show a picture of it. The flight hardware is fully built and integrated and tested, sitting in a clean room at LASP right now. It's an infrared camera that makes panoramic images from the surface, and we do this over and over again at a landing site near the South Pole. It's a multi-band imager, so we get both compositional information and also this critical information about the distribution of these micro cold traps on the surface. The resolution is less than a centimeter close to the lander. This just summarizes the specs on the instrument. So we expect L-Sirius to get some of the first thermal, maybe the first thermal infrared images from the lunar surface. It's now a race because we were also selected to provide an almost identical instrument for a rover mission called Lunar Vice, which is landing on the near side of the moon, that now will be launched about the same time. So we had L-Sirius, you can see the flight instrument there. The reason it's done and we're not launching until 2025, 2026 is because the commercial lander provider that was supposed to take ours and the other instruments to the moon went bankrupt. Okay, and so back in about a year ago, we started to hear rumors that things weren't going well with this company, and then all of a sudden we saw in the news that the company had gone bankrupt. So NASA remanifested all of those instruments onto another mission. We couldn't be more excited about our mission, so we were manifested with the Prospect drill, which had originally been planned for this Russian lander. It's going to drill down 1 meter deep beneath the surface and for the first time get down to the level where we might actually see the actual tip of the iceberg, basically. I wanted to wrap up with some of the key research avenues that my group is going. So one of the things that we realized in planning for missions, including L-Sirius, is that we have to do a detailed accounting of the three-dimensional topography and radiative transfer on the lunar surface to account for the temperatures of all these small shadowed regions. And so we've developed these codes that can do this based on hardware-accelerated ray tracing that was pioneered in the gaming industry, basically, but we use the same kinds of techniques coupled to our heat transfer modules that allow us to calculate temperatures on the surface and in the subsurface. We've been applying this also to other bodies, including Europa. Kaya Sorley is working on that as part of her thesis. Okay, so last couple of slides. Going back to Antarctica then, what do we envision for the future of lunar exploration with humans? It might look something like McMurdo. So McMurdo Station is a permanent base in Antarctica. There's also a base at the South Pole. And so we can imagine that the delivery of hardware to the lunar surface could be targeted towards building up this kind of infrastructure for a sustained human presence on the surface. And as you build it, it becomes easier and easier to go back, basically. And so you can see the dramatic change in McMurdo over the years, the decades, and almost centuries, going from this rudimentary camp to this major scientific operation. And I think a key thing here is that this is science-driven, and it's incumbent upon us as scientists to be involved in these kinds of missions because they should be driven by science at some level. And in fact, once we have a permanent station, the science opportunities will only grow. I also wanted to make a quick pitch that I think students have opportunities to be involved in this at all levels, and we've done this through a program called Ad Astra Academy, both here at CU and abroad. These are pictures from our Brazil version. The capstone project for this program is that the students who are about middle school age get to participate in looking at real data from real missions, and one of my plans as the PI of L-Sirius is to involve students like this in the actual observations from the lunar surface of our instrument in real time, and so we'll look forward to doing that. So I think the lunar poles are the next frontier in exploration, particularly with humans, and we should ensure that these outposts are developed with science in mind, with a scientific purpose for the year-round presence of humans on the lunar surface, and I think we can and should involve students at all levels. Thank you very much.
All right, thanks a lot, Paul. It takes several days to get to the moon, but we were able to get there and back in about 55 minutes. So there are about 3 minutes officially for questions right now, and I'll make sure that I denote the official end of the time. with priority for students for first question. Great. People on Zoom cannot hear you. Yeah.
This is, first of all, great talk. Thank you. This is maybe different sort of question from what others might ask. I'm in solar physics, and so all of this, for the most part, is new and interesting to me. You mentioned that the 13 out of 13 CubeSats were unsuccessful in that one mission. What goes wrong, if it's not too painful to recount?
Yeah, no. Yeah, it's enough time has passed. We can talk about it. The propulsion modules failed in several cases in different ways. In the case of Lunar Flashlight, we were using a new technology called green monoprop, and it was a technology meant to keep astronauts safe if we were to use a propellant that could be toxic, that could adversely affect astronauts. So we were using this new system. I think what actually went wrong, based on the analysis that I've seen from the engineers, is the propulsion unit was 3D printed, and that had never been done before at this scale. And it was not tested enough because we, again, ran out of time for testing and money, to be honest. So these were all very low budget operations. I can't speak on behalf of the other CubeSats. You can look up, there are people who love this kind of stuff. So there on the web, you can find all kinds of detailed information on how these failed, but I would say propulsion was the most common issue.
Thanks. Another question. We'll go here.
Yeah, great talk. It seems unlikely that Mars would ever be terraformed. Bruce Zukowski has been quite persistent in that regard. Can the same thing be said about the moon?
Yes. Yeah, so the issue with Mars terraforming is the lack of enough volatile material to produce a breathable atmosphere, basically. And Bruce has published on this by looking at that in some detail. Same thing is true on the moon, that even if you were to vaporize all of the ice that we think is there, and even using optimistic assessments, you may get a collisional water atmosphere, but it's not going to be breathable. So the best thing we can do is to build habitats, basically. Another paper we have two papers on the idea of using lunar lava tubes and caves as habitats. Those might actually be very good habitats, even though our models show that they are not very good places to trap water. So we shouldn't expect ice caves, but you put a lid over the the tube, and it's actually a fairly good place to survive and avoid the harsh radiation environment of the surface.
Okay, with that, we've reached 1:15, so let's do two things. First, let's thank Paul one more time. And if you have questions for Paul, feel free to come down, but you're not going to beat me because I'm going to ask him to compare and contrast Mercury before you ever get here. Okay.
And I'm holding sort of informal office hours from 2:30 to 3:30 today in my office, D321 in Duane.